My goal here today is to look at a particular type of function, a function with a particular domain, and that's a sequence. But it sounds to me like the intuitive idea of a sequence shouldn't particularly be a function. What's a sequence? Intuitively.
Set of numbers in an order?
In an order. So this is what differentiates it from a set. I have to put it in order, right? So if I'm going to put it in order, there's a first, a second, a third, a fourth. There's my function. So a sequence is really a function from the natural numbers to our set. It's an ordering, right? So f of 1 is element 1. F of 2 is element 2. Wait a minute. Our textbook uses 0 as a natural number, so we would have f of 0 as S0, and so on. So our idea of a sequence in an order then becomes a list in order.
Since our book counts 0 as a natural number, should we include that in all of our homework going forward?
This is one of those things where I'm going to go only if it makes sense. Because technically, it's a function from the natural numbers to S, but I could make the domain a subset of the natural numbers and thus start at 1, couldn't I? So instead of S, sometimes we'll use A. So we'll have A0, A1, A2, A3. And then the terms in my sequence are AI. Now that would indicate a set, right? So in order for me to say, oh, this should be in an order, I'm going to say, oh, well, we're letting I start from 0. And that's like our sum, right? Our product, our notation for the ands and the ors with the loops. This is a loop. Start at I, count up by 1, and just keep going. I put infinity at the top there. Don't panic. We can do infinite sequences. We can do finite sequences. It's literally your choice. And it depends on the circumstance of what we're doing. The way we describe a sequence, we could say, I want to describe the nth term in the line. So I could give a formula and Emily, here's a case where I absolutely cannot start with I equals 0. I'm doing 1 over I, right? Dividing by 0 makes my calculator go, I don't want to do that. But again, I could enumerate all of the things in this sequence. I could say the sequence AI, I starting at 1, looks like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. Just like with our set notation, I only want to use that ellipsis that's set at 3 dots if the pattern is clear. You did a bunch of this sort of crap on the SATs, right? What's the next number in the sequence? Find the pattern. Ugh. I hate those. But I don't have to have a formula. I used this term before, so I'm going to ask you to remind me what it means. What does it mean for a number to be prime? Beth? Right. So the ith prime number, the first, the second, the third, I go through my list. I can say, hey, I know that this list starts 2, 3, 5, 7, 11, 13, but now I have a problem. The problem is I know what the next number is. I don't have a formula to find it. There is no known formula for PI at all. So I'm stuck. I know, hey, just keep listing primes. I know what those mean. I can tell you whether a number is on the sequence or not, but I don't have a way of finding the next prime number formulaically like I did up here. It's unfortunate, but just like in our set, a description will suffice. Questions? Some sequences are particularly useful. An arithmetic progression is a sequence where every two numbers have the same difference. In other words, if I look at the ith term and I look at the one before that, the difference between those two is some constant. D for difference. Ian, give me a number. 1. Dom, give me another number. So I could go 1. 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. 17, 21, and so on, right? My difference is 4. A0 was 1. D was 4. If I asked you for the 23rd number in this list, could you find it without doing all of the 22 in front of it? How?
Just take the difference and you would add it to wherever and you're at, or number 1, you could add it to the first spot. And then you would times the difference times however many spots you wanted to go to.
So I don't have to add it the first time. I just have to know how many times I'm going to add it total, right? So if I say that A0 is 1 and I want the 23rd number, the 23rd number would be A22 because I started at 0. Well, that would be 1. And then I would have added 22 times. Oh, I can do that in general. An is going to be A0 plus n minus 1 times the difference. I don't have to just do it step by step by step by step. I can do it all at once. So I have a formula for the general term. By the way, let me think about this like it's a function and graph it. What's the graph of that look like? Let's use our particular example.
X plus 4.
It's a straight line, isn't it? Slope is 1, Every time I go over, I go up 1. No, every time I go over, I go up 4. My slope is 4. Every time I go over 1, I'm going to go up by 4. My y-intercept is going to be 1. So this is a discrete version of a line. It's a bunch of dots arranged in a straight line pattern. Okay. I think. Questions? Talk to me. What if instead of adding, I multiply? So now instead of adding, I multiply. AI divided by AI minus 1 is some ratio. Or if you'd rather, AI is R times AI minus 1. So I pick my number and then I multiply with each step. I'm going to use the same two numbers. I'm going to start with A0 is 1, and this time the ratio is 4. So my sequence goes 1, 4, 16, 64, 256, and keeps going. I just keep multiplying by 4. Let's see. 1024, 4096, 16380. We can keep going as far as you want, right? What's the shorthand for repeatedly multiplying in algebra? Exponents. So I can think of this as 1 times 4 to the first, and this is 1 times 4 times 4, that's 4 squared, 1 times 4 cubed, 1 times 4 to the fourth, 1 times 4 to the fifth. What's the 22nd term in this number, in this list? 22nd term in this list. Sorry, 23rd term. A22.
1 times 4 to the 22nd.
Because every time I have to multiply, right? So it'll be A, the first number, times 1 less multiplication. Huh. Interesting note. If I kept going, what's going to happen to those numbers? Boom, you're gonna blow up, right? What happens to the picture? This isn't a straight line anymore. What's this graph look like? What was that, Blaze? Almost. A parabola has the same power everywhere, right? It's x squared. But this time the power changes as I go forward. What's that graph look like?
It starts as an angle up, or as a line up, and then it starts swooping straight up and down. So it goes like that.
I know the name for this thing. We're not looking at this side though. I want to look at this side. It's not truly a parabola because it keeps getting steeper and steeper. The power keeps getting bigger and bigger. What's that graph called?
Is it called like an exponential graph?
It is called an exponential graph. Normally we use E, right? E to the something, but it's whatever my ratio is. The base in this one, the power, the thing I'm taking the power is 4. So it'd be 4 to the X. Okay, that's an exponential growth. Exponential growth. Wait a minute. Something about this from back in calculus. We started doing derivatives. Something about exponentials and derivatives. That was the reason we use E, right? What's the derivative of E to the X? E to the X. That's what's special about E. It's the base that makes that just right. But in general, you'll see when we get to the chain rule that this is actually easier to take the derivative of in general, regardless of what the base is. Populations grow exponentially. You think about population growth, when you've got a lot of people, have a lot of children. Got a lot of animals, a lot of bacteria in the dish, whatever it is. Populations grow in this fashion. Food resources grow linearly. Every time we have expected population to outpace the rate at which we grow food, we've changed the way we grow food and changed the slope of that line. A historian, social scientist by the name of Malthus predicted at several different points in time, I believe it was the 1850s when he first wrote the paper, that at some point the population of the Earth would be too large for the food capability of the Earth to support it. In 1856, he predicted this would happen in about the 1900s. He was wrong then. Paul Ehrlich in the 1970s predicted it would happen by 1995. He was wrong then too. So we keep changing the way we grow food to avoid this sort of Malthusian collapse. Questions?
Because that exponential one goes straight up and down eventually, are we going to be using or not almost straight up and down?
We're going to get some really big ass numbers.
Are we going to infinity with that?
Only as I keep going, right? So my problem is this is a function of the natural numbers. Technically, the natural numbers don't end. If I cut it off at some point, then there is a top to it. Biggest integer I can create on my computer is 64 bits, right? I can do a quad precision, right? That's 128 bits. That's a big ass number. It's still not infinity. So there is a limit practically to how big a number I can make. But there's no reason to think of it as having to stop. Unless I'm constrained by something. Other questions? Yes, sir.
You're explaining this, but I didn't know when you use that equation compared to the one for.
So somewhere it's got to say either arithmetic or geometric in it. So the fact that I'm using this formula only works when I know I'm doing a geometric progression. I can only use this one when I know I'm doing an arithmetic progression. So those are restricted cases. A lot of sequences don't have named descriptions like that. And so, like our prime number sequence, I don't know what the next one is. I don't know what the name of that is. Like this list of reciprocals. Maybe that has a name, maybe it doesn't. I don't know at this point. I do know that there is a name for that, and we'll get to it. Musicians. The name for this comes from music. So different sequences will get named because of the way we do them, or what caused them to come into existence, but these are the only two names I have at the moment. More questions? A finite sequence can be thought of as a string. I want the first 17 numbers Okay, here's the first one, the second one, the third, 17th, I'm done. So in that case, the 0th one would be an empty string. Don't you have a pointer to an empty string in databases? It's a pointer to a void, /dev null. It exists. It makes sense to have a 0 be 0. Some sequences are defined in terms of themselves. I give you a starting point, and I say the way we're going to proceed is to define the next number from where we are. So I've given you the first term in my sequence, A0. A0 is 2. To get the next one, for any n bigger than 1, I'm going to use this formula. The n is the subscript. So A1, how do I get A1? According to this rule, A1 is A0 squared. Oh, I know that. 2 squared is 4. What's A2? Because it's A1 squared. A3 is A2 squared. Crap. 16 squared is 256. A4 is A3 squared. So what's 256 squared? You own calculators, people. Don't do this in your head. Right, do it by twos. 5, 12, 10, 24, 20, 48. 4,096, right? No, I'm off by a set. I'm off by more. 65, 536. 65, 536.
I got scared because you said such a number that was way off from mine, and I was like, did I just?
No, I did it wrong. No, I did it wrong. It's okay. I multiplied by 16, not by 256. For those of you who are computer scientists, that number should stick in your head. 65,536 is 64K. It's the number of possible memory slots in 64K. They're all powers of 2, people. The next one's going to be even bigger. What's 65,536 squared? Mommy.
4 million.
Yeah, these numbers grow outrageously big really quickly, right? This is a recurrence of depth 1. What do you think that means?
To get the ith element, you only need to know the I minus 1 element.
I only need to know 1 back. That's also why I had 1 starting value and then can proceed from there, right? A recurrence can be of any depth we want. Here's a depth 2 recurrence. I'd like the first 10 numbers. I'd like to get to A10. Sorry, F10.
5, right? Fibonacci.
Aha! 0, 1. The next one comes from adding these two. F2 is F1 plus F0. What's F3? Oh, it's F2 plus F1. That's 1 plus 1, so 0, 1, 1, 2. The next one is the sum of these two. Add those two to get this one. Add these two to get this one. Add these two to get that one. I just keep building up in pairs. 5 and 8, that's 13. Fibonacci? Who the hell is Fibonacci? Santino, here's another spot. I have a name. Where the hell did this name come from? Who's this dork? Fibonacci is an Italian surname. Leonardo of Pisa, son of Boccaccio, Fibonacci, wrote a book called Liber Abaci, the Book of Counting. In the 1600s-ish? I don't remember the exact year. But the goal of this book was to introduce to the Roman and Latin and Italian-speaking population Hindu Arabic numerals. Because at this point in time, we were still conducting all of our math in the Western world in Roman numerals and in words. How many of you have written a check at some point in your entire life? What do you have to do in addition to writing out the numbers in the little box? You have to write out the word for the number. Why? Because the Italians didn't trust these newfangled numbers, and if you wrote out a number, I knew what it was. I wish I was making that. All of mercantilism happened through Venice, through Italy, and that's where Fibonacci wrote his book. It would be nice if there were a formula to generate these numbers without having to work backwards, right? Because if I want the 100th number, we're going to be here for a while. In 1843, a gentleman by the name of Binet showed that this particular formula always returns the nth Fibonacci number. Right. 1 plus the square root of 5 over 2? 1 minus the square root of 5 over 2? Where the did that come from? Wait a minute. Number plus or minus the square root of the same thing over to, I've seen that before. What does this sort of setup remind you of? Algebra class. Quadratic formula, right? B plus or minus the square root. There's a relationship between the fact that this is a depth 2 recurrence and a quadratic equation. We'll figure out what that relationship is in chapter 8. We have some time. But our ability to find a closed form for our recurrence equation is nice. This is a non-recurrence version. Now, if I want the 100th number, I just plug in 100. Done. On the other hand, doing the recurrence, I have to do all 99 in front of that. That takes up a lot more computing power. Finding non-recurrent forms is useful. It isn't always obvious. Here is a depth 1 recurrence. Let's write out the first 6. So I want A1 through A5 because I have A0. A1 is 3. 4 minus 1. What's A2? Previous term minus n. The n doesn't have an a with it. That's okay. I can use n. It's the counter in my loop. I can do this. What's A3? Okay. I would like to know if it's possible to find a closed form. A non-recurrence formula. A formula that doesn't depend on what came before. But I think the way this is written is the problem. So I'm going to go back and I'm going to write this list again. But I'm going to write it slightly differently. Remember, we started with A0 is 4. And then I said, to get A1, we took 4 minus 1. I'm not going to simplify it. I'm going to leave it like that. A2, what does A2 do? It takes this number and subtracts 2. What's A3 do? Beth?
4 minus 6.
Well, but I'll write it. I take the number before and I subtract n, right? I take the number before and subtract n. Hey, wait a second. I'm subtracting all this junk, right? Let's factor out the minus sign. I could write this as 4 minus 1 plus 2 plus 3 plus 4 plus 5. Couldn't I? What's AN? Oh, AN is 4 minus 1 plus 2 plus 3 plus all the way to n. There's a closed form, not a recurrent form. I don't have to know A99 to get A100 anymore. It would be even nicer if I knew a quicker way to do that addition. I don't. Yet. Yet. Example 11, page, I think 169, shows the process of compound interest. Compound interest is a geometric progression. Because you earn interest on the interest you've already earned, right? So you keep multiplying by more and more numbers. Geometric behavior. Page 169, example 11. I don't know if I mentioned this in this class already or not. But my PhD work was about sequences of complex numbers. This is my buddy Mandelbrot. Here's the deal. Pick a number. In the complex plane, that number could have a real part and an imaginary part. That's a dot on this plane. I'm going to do x squared plus the number you picked. I'm going to take what comes out and I'm going to put it back in. I'm going to make a feedback sequence. Let's pick the number 0. Now I'm going to start with 0. 0 squared is 0. I add 0, I get 0. This is boring. I'm going to get 0, 0, 0, 0, 0, right? Let's color that dot black. Pick another number. -1. Take 0. 0 squared minus 1 is 0 squared minus 1. -1 squared minus 1. I go from 0 to -1. I go from -1 back to 0. I get caught in a loop. My sequence goes 0, -1, 0, -1, 0, -1, 0, -1. It never gets any bigger. It's caught in a loop. Color it black. Every spot up there that's colored black corresponds to some sequence starting at 0 that gets caught in a loop of some type. The fact that that loop had 2 numbers in it means that we are in this circle over here. The first number I picked, 0, got caught in a loop of length 1. It went 0, 0, 0, 0. That's in this curvy shape here. If you're up here in this little blob, you're a cycle of length 3. If you're in this little blob, you're a cycle of length 4. 2, 4, 8, 16, 32. They all stack up on each other. See that out there? There are little bitty copies of the whole thing. Way out there. So much neat there. But it's all based on, does my sequence explode or does it stay bounded in some loop? For the record, Mandelbrot worked for the IBM Watson lab in 1980s. So this is new math. There are some sequences we see a lot. What pattern do you think that is? squares. Three cubed is 27, four cubed is 64, five cubed, six cubed. On we go. Do I expect you to memorize and recognize these? Oh, hell no. Take a look on page 171. Here are several sequences that we will see pretty frequently. Squares, cubes, fourth powers, the Fibonacci sequence, powers of 2, powers of 3. What's that one again? My factorial. 1 factorial, 2 factorial. You notice those get really big really quickly. I don't want you to memorize this table. I want you to put a Post-it note on this page, put a bookmark in your PDF, be able to find this. But the purpose behind this is that if I give you a sequence and I say, can you find a formula for this sequence? Well, then I have this as a cheat sheet, kind of, a template to go off of, to look for patterns. So here's an example. Let's find a pattern for this. Now, because I gave you that list on page 171 to prime you, I'm going to tell you right now, this one isn't related to those lists. So I've cheated and broken away from that list to start with. But my first question is, does this fit a pattern I already know, Santino? Does that look like it might be arithmetic? Does it look like it might be geometric? Let's compare the terms to each other. Is there a gap that's the same going from one to the next, to the next, to the next? Some of you are nodding and some of you are holding your head like, oh my God, you just blew my brains out my ears. 5 to 11, I added 6. 11 to 17, I added 6. 17 to 23, I added 6. I see a common jump here. So if I call this A0 and this A1 and this A2, then I can say, oh, A0 is 6 and the nth term, I'm sorry, A0 is 5. And then AN is 5 plus however many 6s I needed to add. Does that work? Well, the second term would be adding 2 6s, 12 and 5 is 17. A3, A4, A5, A6, the pattern matches what I see given to me so far. Here's another sequence. Bleh. I'm pretty sure this is not arithmetic. To get from the first to the second, I added 12. To get from the second to the third, no, I did not add 12 again. That's not right. So let's look at page 171. Let's look at that table that we were given earlier and see if something is close. And at the same time, let's look, it's not arithmetic, could it be geometric? To go from 2 to 14, I multiplied by 7. But to go from 14 to 62, I didn't multiply by 7. Not truly geometric. On the other hand, what's 62 divided by 14? What's the ratio between those two? Grab your calculators, divide. (62 over 14 is). What's 254 over 62? (1022) divided by 254. (4.02). These are getting closer to 4. So maybe this is related to multiplying by 4, even if it isn't exactly multiplying by 4. On our list, there are powers of 4, aren't there? Read me the first 5 powers of 4.
16, 81, 256, 625.
No, those are powers to the 4th. I want 4 to the something. Is that on my list? No? Then let's do that one. Let's look at powers of 4. It's not quite multiplying by 4. What's multiplying by 4? 4, 16, 64, 256, 1024, 4096. Wait a minute. How much am I off by? I'm off by exactly 2. I'm looking for patterns. I'm going to try my arithmetic. I'm going to try my geometric. I'm going to try and say, well, it's not quite. What is it close to? The following is a guaranteed going to queue up thing. If you don't have enough terms in the sequence, there are multiple answers to this. So I'm going to cheat.
Somebody did all this for me.
What are computers really good at? Pattern matching. You get a new start of a pattern. If I give you that list, what pattern do you think that is? I haven't the foggiest idea. But if I ask this to search the database, there's the start. 1, 2, 3, 6, 11, 23, 47, 100. It appears in this sequence. It also appears in this sequence and this sequence. And there are so many different versions of ways to get this sequence. It could be part of so many different things. Unless finding the sequence is really obvious, I'm going to use this. OEIS, Online Encyclopedia of Integer Sequences, oeis.org. I'm not done with this section because there's more to come on Friday. I will see you all then. Have a wonderful rest of your day.